quantum mechanical calculations of a physical property is based on some postulates. These postulates cannot be derived or proved. Rather, they are taken as axioms or taken as granted. Today, in my lecture 6 in the series of quantum mechanics, I shall discuss the quantum mechanical postulates, and today I give some idea about the postulate 1, construction of quantum mechanical operators. How the quantum mechanical operators are being constructed of a physical property. This we know every physical property or observables have its corresponding quantum mechanical operator. This operator operates on this function, wave function of this system to give this property itself. All these operators already I have told, they are linear and the Hermitian. Otherwise, the operator that represent the physical property is not real, may not be real. There are so many properties of a quantum mechanical systems, say position, say momentum, say kinetic energy, potential energy, total energy, angular momentum, and so on. First of all, I try to define or how the quantum mechanical operators of these properties could be constructed. There are set of rules. There are set of rules for construction, for constructing quantum mechanical operator. First rule: the physical property whose operator we are going to construct, that physical property is to be expressed in the physical property whose operator we are going to construct, that physical property has to be expressed in terms of the Cartesian coordinates and corresponding momentum. We know that every physical property of a system could be expressed in terms of this position and momentum. So the first one, the property is to be expressed in terms of Cartesian coordinates x, y, z and momentum Px, Py and Pz. Then these Cartesian coordinates of the position and momentum are to be expressed in their corresponding operator. This is second one. Position, say it is q, and corresponding momentum, say pq, are replaced corresponding operators. This third one, position operator, is a multiplier operator, and say Q. Q is simply the Q cap operator, and it is multiplied by the variable itself. Then fourth one, the operator for this momentum is expressed, say PQ cap equal to minus I H cross dy dq. I is the iota, I equal to root over of -1, and H cross the reduced Planck's constant, and this is equal to H by twice pi, and this dy dq is the first derivative with respect to q. Now I shall formulate this operator for this momentum. The operator for this momentum is formulated on the basis of the classical differential equation of a standing wave, and this formulation of a PQ cap. The differential equation for the standing wave is d2 psi by dx square equal to minus 4 pi square by h square into psi, in whenever this wave is moving along this x direction. So this lambda, according to de Broglie relation, this lambda is replaced by h upon px. Along px is the momentum, linear momentum along this x directions, and this one becomes 4 pi square and px square divided by h square into psi. Psi is the wave function, and this I can now replace this -1 equal to I square and h by twice pi, which is called the reduced Planck's constant, is h cos. Then it becomes I square px square divided by h cross square into psi. Or we can write h cross square divided by I square into d2 by dx square psi equal to px square and psi. This one is an eigenvalue equation. This one is an eigenvalue equation. And you know, my dear students, this psi is the eigenfunction of this operator with this eigenvalue px square. So we can write the px square corresponds to the operator h cross square divided by I square d2 by dx square. Naturally, then px cap operator of this px is equal to the root over of this one, h cap divided by I d by dx. This one I can write, say, minus I square h cross square divided by I d by dx. I square also minus 1, minus 1, minus 1 plus 1. See, the result remains the same, then I can cancel 1I. So this px cap becomes equal to I h cross d by dx. Similarly, say py cap, you can write minus I h cross d by dy, and pz cross equal to minus I h cross d by dz. So these are the operators of this px, py, pz in quantum mechanics. Now I shall construct some operators corresponding to physical properties. Operators corresponding to some physical properties. Of this system. First, I construct the kinetic energy, which is symbolized by T, kinetic energy operator. Kinetic energy T equal to, in terms of this momentum along this x direction, px square divided by twice m, and this is the kinetic energy in terms of this momentum along this x directions. But we know this px equal to minus I h cross d by dx. So replacing this px square in terms of this operator, we get this kinetic energy operator equal to minus h square divided by twice m and d2 by dx square. So the second one, the energy operator, total energy operator. This is a very vital total energy operator, sometimes called the Hamiltonian operator, according to the name of Roland Hamilton, mathematician in the 18th century. Operator. This total energy is equal to kinetic energy plus potential energy. So this one equal to this T and plus V. So the operator for this total energy is Hamiltonian operator, and this one equal to T cap plus V cap. These are the operators. But already I have formulated the operator for this kinetic energy is equal to minus h cross square divided by twice m and d2 by dx square and plus this v cap and this x. V potential energy depends on the position along this x axis. In 3 dimension, in 3D, this h cap now becomes equal to minus h cross square divided by twice m, and instead of d2 by dx square it will be del square Laplacian operator plus v cap, and this is dependent on x, y, z. And we know this Laplacian operator equal to del 2 by del x square plus del 2 by del y square plus del 2 by del z square. Now I formulate the Hamiltonian operator for some systems used in quantum mechanics. Hamiltonian operator for some systems, say quantum mechanical systems. First, I shall construct this particle in 1D box. Here the potential energy is equal to 0. So the Hamiltonian operator is only due to the kinetic energy, and this one becomes minus h cross square divided by twice m into d2 by dx square only. The second one-dimensional simple harmonic oscillator, here v equal to half kx square, and in this case h cap equal to kinetic energy minus h cross square divided by twice m, is the kinetic energy operator, d2 by dx square, and this potential energy equal to half kx square. And this 3-1 hydrogen atom, this third system hydrogen atom, here v equal to minus e square by r, and it is the 3-dimensional motions. So this h cap in this case equal to minus h square divided by twice m, and it is Laplacian operator del square minus e square by r. This is the potential energy. And this fourth one, a rigid rotator, rotating on the xy plane along z axis, and potential energy equal to 0. So this h cap in Cartesian coordinate minus h cross square divided by twice m, and here del 2 by del x square plus del 2 by del y square, and here the potential energy equal to 0. In polar coordinates, only the horizontal angle is changing. So h cap equal to minus h cross square divided by twice m, and d m r square, and it is d2 by d phi square. Phi is the horizontal angle. We know this mr square equal to the moment of inertia. Moment of inertia. So it could be written as h cap equal to minus h cross square divided by twice I and d2 by d phi square. I have already discussed the kinetic energy operator, total energy operator, which is called Hamilton operator. Now I shall try to construct the angular momentum operator. Angular momentum operator. This property, angular momentum, is a very important property for this rotating system. And this L, this angular momentum vector, is the cross product of this position and the linear momentum. If I vector, j vector, k vector are the unit vectors, along x, y and z direction, then this one could be written as I vector Lx is the scalar quantity, plus j vector Ly plus k vector and Lz, and this one equal to, these are position in terms of this unit vectors, I vector x plus j vector y plus k vector z, cross product into I vector px plus j vector py plus k vector pz. These are taken the process to express this Lx, Ly, Lz in terms of their position and momentum coordinates. And whenever these products are being done in terms of this vector product I, j, k, x, y and z, here px, py and pz. This one is I vector, and here I vector ypz minus zpy plus j vector, whenever j vector, and it is j vector, it is zpx minus xpz plus, whenever k vector is used, this one equal to xpy minus ypx. So equating with these two, we have this Lx equal to ypz minus zpy. This Ly equal to zpy minus Z ZPX 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 minus XPZ, and LZ equal to XPY minus YPX. So far we have expressed the linear angular momentum Lx, Ly, Lz in terms of the Cartesian coordinates and the corresponding momenta. If we replace this momenta by their operators, we get this Lx cap operator for this Lx angular momentum equal to minus I h cross, and this will give you this y and del y del z minus z into del y del y, and this Ly cap equal to minus I h cross and z del y del x minus x del y del z, and this Lz cap equal to minus I h cross, and this one x del y minus y del y del x. So these are the corresponding operators. This operator plays more important part, that it is the angular momentum operator when the particle rotating along this xy plane, on the xy plane along this z axis. It is also written in polar coordinates minus I h cross and d by dy. Now I like to show how the operators are expanded. Whenever the operator I like to expand, we have to add some functions. Already I have told an operator itself has no meaning, but whenever the function is added to this operator, it becomes meaningful. So first one, this operator x dy dx whole square, this is to be expanded. So psi, the function is added, psi is a function of x, and whenever we are doing these operations, then x dy dx, it is the successively two operators operated on this function psi, and this one remains intact, and this x and d psi by dx. Then again next step x, and whenever this differentiation is done on this multiplication of these two quantities, it will be x d2 psi by dx square plus x to the respect to 1 and d psi by dx. So multiplying x square d2 psi by dx square plus x d psi by dx. If we take this psi common, then d2 x square d2 by dx square plus x d by dx. This psi common, then operator is expanded in this way, plus equal to x square d2 by dx square plus x d by dx. In a similar fashion, I can also expand several operators. Then this one, here the terms are exchanged. dy dx into x square, the value becomes different. X square d2 by dx square plus 3x dy dx plus 1. And when dy dx plus 1, this one is 2, and this one I can write this 3 dy dx plus x whole square equal to x square d2 by dx square plus 2x dy dx plus x square plus 1. These are given for my dear students to exercise at home. So this is all about the postulate 1, how the operators, quantum mechanical operators to be constructed of a physical quantity, physical properties or the observables of this system. And in my next lecture, I shall go for the postulate 2, how the constant value or characteristic value of this system would be evaluated by using this eigenvalue equation. Thanks to you all who are watching this video, and I request all of you, if you like it, then please subscribe and share.